Okay, thank you. Thanks. Let's pick up from where we left off yesterday. There was one particular plot that we had looked at. This was for GW 150914, which was showing the posterior distribution of the source frame masses, M1 source and M2 source. And you can see the masses at the bottom listed as in terms of solar masses and also on the y-axis. And so there was some back and forth about whether what kind of a degeneracy is this? Is Chirp mass or total mass degeneracy? And so what I did was, while you are working on the tutorials, oh, I need a clicker. Where's the clicker here? Let's see. It should be here at the podium. No, it's not. Oh, it is there. Maybe the drawer. Okay. Thank you. Okay, so when you are working on the tutorial, I just tried to make this plot where I'm showing, again, the same kind of axis here, 20 to 35, 25 to 50. And then I took the parameters of GW 150914, and I asked, okay, if it is chirp mass, then what kind of degeneracy you should get? And if it is total mass, what kind of degeneracy you should get? And you can see, like, it's partly follows the blue line somewhere, partly follows the red line somewhere, so it's difficult to say. And this is because if you go to higher and higher mass events, then as Prayush said, you are indeed sensitive to the total mass, and this lies somewhere at the edge. And so it's neither exactly the chirp mass nor totally the total mass. And because I remember making this kind of a plot, the blue one, I had never made this M1 plus M2 plot, but this is quite useful. And so the idea here is when LIGO has finite frequency bandwidth, right? And so it can only see events which occur in that particular band. If you have the initial cycles of the gravitational wave event, which fall in that band, and for a long time, then it will be mostly sensitive to the chirp mass. But if it is at the end, towards the end only that you see it in your band, and a lot of the signal to noise ratio is only related to that end part, then it is the total mass that you're more sensitive to, if I'm not wrong now, right? Yeah. And so if you look at, I mean, this becomes a little bit more obvious. This is plots picked up from the LIGO LVK papers by Prayush and sent to me. So this is low mass events where you can clearly see the chirp mass kind of degeneracy. You go to higher mass events, it's roughly somewhere in between, even higher than it is more and more towards M1 plus M2. Okay. And so these kind of plots, they help you to see. So this is chirp mass as a function of effective in-spiral spin. So let's forget about this y-axis here. But if you see something which is vertical, then it means that the chirp mass is very well constrained. Whenever you see some things which are going a little bit off, like diagonal and so on, then it means that it's not exactly necessarily just the chirp mass that it is constraining. So here is, for example, total mass as a function of the mass ratio, M1 divided by M2. And again, when you come to larger and larger masses, you can see that this is getting more and more vertical. So it's the total mass which is sensitive to. There are many, many more other events which are lying here, and it's like a combination. Right? And so we are talking about how to separate out some of these events and whether we can use these kind of events to try to get at better cosmological constraints. So we'll come to that later. How exactly to do this? How exactly to use the mass distributions in order to constrain cosmology? Hopefully in today's class. Okay. So this was from yesterday. Today and in the next few days, we will be dealing with how to analyze the data, right? And so you will see some gravitational wave data, and you would want to get out the constraints on cosmological parameters out of it, right? So ideally, what you want to do is to ask for the probability distribution of the parameters of your interest given the data that you have. Okay? And these kind of questions can be better dealt with if you go to a Bayesian formalism, because oftentimes it is harder to write down the posteriors, but easier to write down something called a likelihood, where you can ask, given my parameters, what is the probability that I see the data that I have? And so the difference between the two comes via something called the priors. And so this whole business will go into something like Bayesian analysis. And so I thought that I should give out some of the most basic probability theorems that are there. And then we will be having a repeated use of many of these equations. And so this should be like a cheat sheet for you. Okay. So the first one is the Bayes theorem. So P of A comma B, the joint probability distribution of A comma B, is given by PA given B multiplied by the probability of B. But equivalently, you can also write it as PB given A times the probability of A. Okay. And so this last equality here is typically referred to as the Bayes theorem. Okay. And this Bayes theorem will become useful because, as I said, what we are interested in is the probability of parameters given the data sets, because that's what you have measured. But it will be easier to write down probability of data given the parameters, right? And so the two will be related, this PA given B and PB given A by this equation. Okay. Then the next thing that we have to know is oftentimes what will happen is you will have a joint probability distribution of a number of parameters. So you will be interested in cosmological parameters, maybe some other parameters also, which determine how the data will look like. These may be nuisance parameters, maybe things that you are not interested in, but they are important in order to predict what the data will look like. If that is the case, then in the end, if you are only interested in A, you don't care about this C, but you have found out what is the joint probability distribution of PA comma C, then you can just integrate out all possible values of C to get to the probability distribution of A. So this thing is called marginalization. This is something which will also come out useful when going from many parameters. So you have posterior distribution of many, many different parameters, but you're only interested in one. And then how do you carry out this marginalization? Okay, so this will be like this. But this PA comma C, I can also write just using this is PA given C times P of PC. So you will also see this kind of marginalizations. Now, when you write any of these equations, in principle, you can even add some information, which may be some kind of prior information that you have, to the right-hand side of all these probabilities. Okay, so let me show you. Let's suppose this prior information is C here. So how do I modify this equation? I can say PA, instead of PA given B, I can say PA given B comma C, some extra information that you have, multiplied by P of B given C will be same as P of B given A comma C, and then P of A given C. Sorry, this should be a given. Similarly, when I want to marginalize and there is some extra information, I can just keep on adding these things here. Okay, so P A given I will be integral of P A given C comma I, probability of C given I, and then DC. Okay, so useful manipulation. Sometimes what will happen is I will take this information and I will divide it out into two pieces, I1 and I2. Okay, initially to begin with, to keep the equation simple, I will club it all together, but then I want to separate it out. So all of these manipulations will come useful at that point of time. Okay, so that's the reason I've written this. So just excuse this typo here. Okay, so with that, now let's go to the bright siren likelihood. And so what are bright sirens? Bright sirens are gravitational wave events where you can detect an electromagnetic counterpart. And This most famously happened in 2017. That's the only event where we know it has a secure, well-known electromagnetic counterpart. So the event was detected LIGO Hanford and LIGO Livingston laboratories. Some maybe in Virgo, basically kind of in a blind spot maybe, yeah. So this event was well detected. But in addition to this, what happened is within the event getting detected in the LIGO laboratories, the event also had an electromagnetic counterpart signal, which was detected in these gamma ray burst monitors that we have. On Fermi, this is in the 10 to 50 keV band. This is, I think, 50 to 300 keV band of Fermi. So there's a gamma ray burst monitor, which is just which keeps on detecting events or the high energy photons that come from this event, from these events. And so you can see that there is there's almost nothing, and then there is a peak that you receive. In addition to Fermi, there's another telescope which is also monitoring. It's in space gamma rays. So this is called the integral, and even in integral, you can see a particular peak that turns up in the background that they receive. Right? And so this happened roughly a couple of seconds later compared to the gravitational wave event being detected on the gravitational in the LIGO laboratories. Okay. Okay, so once we have these kind of localizations, by looking at the difference in the time of arrivals between the Fermi satellites and the integral satellites, now you can start to localize these things. You know, I talked about how if you have multiple observatories, you can start to localize based on the time delay, right? So in this case, even with this small differences, you can start to localize things, and also, of course, using the LIGO laboratories as well. And so if you just take the LIGO contours, I think, let's see, where are they? One of these, I think, okay. So I think these green ones that you see, these are the LIGO contours only. So only the LIGO labs. Then you combine it with Virgo, then you get to the green contour. Then you take the Fermi and the integral together. This, I think, is the integral. This is Fermi. You combine all of these things together, you lie somewhere here. And so this was the localization region that was identified for this particular event. So you would say that, okay, that looks like a very good localization, but it was still a large area. There will be many, many galaxies which are in this particular area. So what you have to do is you have to go and target each of these galaxies and try to see whether you can actually see an optical counterpart of this event. Well, there was one more thing that I wanted to show. This is the challenge of gravitational wave analysis. When you look at this particular event, but in the LIGO Livingston raw data, so here you are seeing the event as it's shown, but in the raw data, it had this massive glitch also in front. Okay. And so it was quite tricky. So these kind of glitches, some of these origins are unknown. And whenever you are doing gravitational wave analysis, you have to deal with these kind of glitches, identify these, try to remove them, or try to cut out data from those regions. So there are many, many efforts which are involved in order to try to identify these glitches and try to get rid of them. Okay, so when you are seeing this data here, that glitch has been removed. Okay, so there's a lot of processing that has been done in order to get rid of that glitch. But even if you ignore that glitch, you can still see this chirp signal. Okay, so so the typical localizations, at least like hundreds of square degrees. In this case, it was a little bit less, I think. But what people do is, yeah. Yeah, so this has to do with when exactly gravitational waves get released, and then there is a jet that forms, so it takes some time. And then after that, the emission is able to escape out of the I mean, of the dense material which is already surrounding this particular binary neutron star merge. Okay, so it takes a few seconds, and then after that, you see the electromagnetic. Yeah.
So is it because of the jet launching time, as well as when the radiation came out of the photosphere of the?
Yeah, so I mean, eventually, this is when the radiation comes out of the photosphere. That's the only time that you can find it out. I'm sorry?
So that 1.74 second, which I am talking about, like the time difference in between the GRV event and the GRV prompt and the GW event.
Yeah.
So it's the time the jet to be launched for the prompt emission, and to get the prompt emission, it should reach the photosphere, right?
Yes, indeed.
That time it should take care of.
Yeah, so it's basically both the jet launching plus the emission reaching the photosphere. What we are seeing is once it comes out, right? Yes. So it has to be both. Yeah. Because but the combination, I'm not sure exactly which one dominates.
Because kilonova and afterglow, it was detected later.
Which one?
Kilonova and the afterglow part.
Yes. Yeah. I mean, but there should be some emission which comes out.
Prompt part actually.
Yeah. So after the afterglow is what you're detecting. In the optical, it's the afterglow that you're
afterglow, yeah. X-ray to afterglow, and in the kilonova it is the infrared and that.
Yeah. So we'll come to that. I'll show you some of these pictures. Okay, so these typical localizations are of these kind of hundreds of square degrees, and then if you have optical telescopes, oftentimes they will have field of view of the order of 1 to 10 square degrees or so. There are better telescopes which have a larger field of views, but then the collecting area is small, and so they don't go as deep necessarily. Okay, so it's a combination. So you have to optimize how exactly you're going to follow up a particular event, a GW event whose localization has been sent out. So nowadays, yeah.
How much does the electromagnetic counterpart event is the
Yeah, so I mean, in this case, this is the only event for which we have seen. So for NSBHS or like binary black holes, we have not seen any event. People don't predict anything from binary black holes. Maybe neutron star black holes should produce something, but since we have not seen anything, don't know.
But from the kilonova emission, we can say one of the participants can be
yeah, indeed. So there were predictions for what kilonova should do, and so that's what people figured out that the whatever you saw, it matched. So I will come to that. I will show exactly what was seen. But first, before that, we need to go into how to detect this event initially, right? Because we have seen the gamma rays, but even with the gamma ray burst telescopes, the localizations are not that great, right? And so you need to go and find the event in order to make sure that you have identified the galaxy in which this event happened. And so once you have a localization region, you need to plan how to conduct these follow-up observations. Okay, and so there are multiple catalogs that have been established for this. So what they have done is they have taken most of the nearby galaxies that are there, and they have measured what are their distances, in what area of the sky they are located, what are the stellar masses that these galaxies have, and so on and so forth. So that you don't spend time looking at low value targets, but you actually target things which are the most high value, the most likely to host your gravitational wave. So a number of these things were done and the search was carried out. Of course, there are other problems that had happened with GW17/17. The localization region was very close to the sun. And because it is very close to the sun, you can only see it just after sunset. And when you are seeing things just after sunset, you can imagine that the locations are pretty close to the horizon. And you cannot really put your telescopes down very close to the horizon either. Right? And so there are lots and lots of technical problems that people had to face in order to look for this particular event. when you, even in the absence of this, when you have a large number of events, so people typically weight the galaxies by their luminosity to decide on the targeting properties. So if you believe that the probability that a galaxy will host a gravitational wave event is related to the luminosity or the stellar mass of this galaxy, then you can do this. And then you can rank order and try to get a list of targets to follow up. Of course, there are also other considerations. For example, some fields in your search area, they may set before, and then the other fields you still have some time. And so you have to optimize because you get a localization region, right? Something like this. Yeah. So there is a high probability region is here somewhere, and then these are the tails. But let's suppose this is the western direction. Ideally, you would like to target these, but there is also some probability that your gravitational wave event lies here. But these fields are going to set early. So you have to optimize how you can target which of these fields initially you should look at. So let's suppose your field of view is something like this, then you have to tile the field, right? And then you tile this field, and then depending upon the rising and setting strategy, will you be able to get to the high probability points or not? You decide, and based on that, you work out an observational strategy. So in the end, for GW17017, there was, after like about 11 hours of search, this particular candidate was found. And so you can see this beautiful galaxy, NGC 4993. And there were images which were taken earlier of the same galaxy. And then when new images were taken of this galaxy, they could find this kind of a counterpart to the gravitational wave event. Okay. You can ask, how do you know exactly that this is the counterpart? Because it's not known that this is just a random coincidence that you saw some transient or not. So that's the part where you need to establish whether the follow-up of this event, whether it gives you signatures which are similar to what you expect from these binary neutron star mergers, right? That the gravitational wave events are trying to tell you about. And so after that, then you can establish. Plus, people also work out the probabilities. So you can ask, what is the probability if you just targeted a random galaxy that you will see a transient coming from the same localization area as where you saw the gravitational wave event, right? And so people try to work all these things out in order to assign for surety that this is actually the counterpart. There were surveys. I mean, after this event happened, all over the world, there were many electromagnetic telescopes which tried to follow it up because it was such a high value target. And so, including there's this telescope called the Subaru telescope at Mauna Kea in Hawaii, and it has a large field of view about a couple of square degrees. But because it has a large mirror, 8-meter class telescope, so it can go quite deep. And so within the localization region of GW17017, it tried to search for all sorts of possible transient events that would have happened. Okay. So as to rule out that this is not the, so as to rule out that this is not an imposter. Okay. So there was a lot of activity which led to the understanding finally that indeed this is the counterpart that we are looking for. Okay. Okay, so there's one more thing lastly that I wanted to explain. So how do you actually search for these events? So the search is done typically that you have images of the sky, which are called template images, okay, which have been made over many, many years of observation. So you have the templates ready. And then you take the new images. After you take the new images, typically the size of the field of view of your telescope, which will be much larger. And so you can imagine that there is an image from from earlier, there's another image much larger than this thing, okay? And then you have to find out where exactly things have changed, right? So it's not a simple task. So typically what people do is they carry out something called difference imaging. which means that they will take the template image, they will take the new image, they will subtract the two. And when you subtract the two, then what happens is the light from the unchanged universe that will just cancel out. And all you will see are things which are either transient or which have moved from one place to the other. So things which move from one place to the other are things like asteroids, for example. So things within our solar system. And then things which change flux. Some of them could be supernovae or kilonovae like this. Or you could have variable stars within our Milky Way, which can also undergo a change in flux. So there are a number of things that can pop out. So you take all of these things and then try to assess the probability, what is what. And so it's a challenging task. Okay. In the future now, you may have heard just recently that the Rubin Legacy Survey of Space and Time, it's a new telescope, the Vera Rubin Observatory as it's called, that has also started taking data. And so now we will have eyes all over the southern sky at least. And so whenever there is a new possibility of a binary neutron star event like this, then there's a good likelihood that you will be also able to see the counterparts. Okay, so and you will get good follow-up as well. So yeah, there are things like this which are ongoing right now, which makes this area promising, and hopefully will detect a little bit more than the only event that we know of. Okay. So that's about GW 170817. So let's look at the galaxy which hosted it. So this is the spectrum of this NGC 4993. So if you look at the spectrum, I think the data is in black, and then there are certain models that you can see in red and yellow. So there are certain features in this spectra which will allow you, so this is this H beta and the O3 doublets. And then there are also these N2 lines. So they allow you to fix what is the redshift of this galaxy. And so once you know the redshift, then you have a redshift, you have the measurement of the distance from the gravitational wave event. You can try to put it together in order to get at the Hubble constant. Of course, the transient was also followed up. Say there are spectra which were taken like a couple of days, and then 3 days, then 4 days, etc. Followed up for a long time. So this is brightness as a function of wavelength. You can see initially there's a lot of emission in the blue, but then as time goes on, this entire emission then goes down, and all you see is the emission coming out in the infrared. So this is exactly what was expected for kilonova emission as well. So this is one of the other reasons why it built more and more confidence that indeed this event is, I mean, the electromagnetic counterpart that we have found is indeed the counterpart of the gravitational wave. There are many astrophysical papers also written about these spectra and what do they tell us about generation of heavier elements than iron. And so you can take a look at that if you want. But what we are interested in is in the Hubble constant. So in the nearby universe, the Hubble law, it reduces to the cosmological recession velocity is equal to the Hubble constant times the distance. Of course, you're in the nearby universe, so you have to worry about peculiar velocities because the galaxy may not be stationary with respect to the CMB frame. And so that's another thing that you have to worry about. So you need to take into account these peculiar velocities. Plus, you have to remember that the velocity that goes into the Hubble law, it won't be the velocity of the gravitational wave event itself, right? Because you may have galaxies which are moving with respect to the CMB frame, but then the gravitational wave event is also not stationary with respect to the galaxy itself. The galaxy has its own velocity dispersion. So the gravitational wave event will be within the galaxy, and then that will also move around. But the velocity that goes here is actually the velocity of the galaxy, but with respect to the CMB frame, taking into account the peculiar velocity. But the frequency shift that you see in the gravitational wave waves, right, the waves that you receive, it will be related not to the velocity of the galaxy, but the velocity of the event itself, right? And so there's a lot of complications. Cosmological recession velocity of the host galaxy, then the peculiar velocity due to galaxy's neighbors, plus the velocity of the GW event with respect to the host galaxy. So this is what will define the frequency shift. Right? So all these things you have to account for before you carry out the analysis. So where is this NGC 4993? So you look at the entire sky, you had the constellation Centaurus and Hydra, and then you keep on zooming in. So you can see that things get quite blurry because the area of the sky that was initially surveyed was not with such a great telescope. But then as you keep on zooming in, you will start to see the Hubble Space Telescope image. So you can imagine how hard it is to localize these kind of events. You're trying to look for a point in such a large region, right, that has changed. And so this was the event. You can see it's quite reddish because this is August 22, so quite a bit later after the event was found. And then as time goes on, you will see that its luminosity has faded. So this particular galaxy that you have, it's not sitting alone. It is also part of a group of galaxies. And this group of galaxies, what you can do is you can measure the recession velocity of these galaxies with respect to the CMB frame. And that recession velocity is about 3,327 plus minus 72 kilometers per second. So this was well measured. So what you do is you take the velocities of all these galaxies and you try to take an average, right? So so that you reduce out any errors because of the peculiar velocities. So the recession velocities are of this order. Okay? But then the peculiar velocity is also something that you measure, and we'll go into roughly how they measure these peculiar velocities. And so there are galaxy catalogs established with the peculiar velocities of these galaxies based on looking at something called the fundamental plane of galaxies. I will try to explain how roughly it works in the slides that come later. But let's suppose you had these peculiar velocities. Then you can see there's quite a bit of uncertainty on this number because you cannot necessarily figure out what that particular Centaurus, so what NGC 4993 is exactly doing. Okay. Yeah? This is just the radial component. Yeah. It's very hard to measure the tangential components in galaxies. Yeah? Yeah. Yes. Yes. So that will be part of tomorrow's lectures. So when we don't have an electromagnetic counterpart, what to do? But today, let's focus on just this. And then tomorrow and day after tomorrow, we'll try to look at events which don't have electromagnetic. But excellent question. Okay, so how do we deal with the data then, right? So what do we have for GW17-OH17, right? So the data that we have is the fact that you saw this gravitational wave event. It has a certain amplitude and a certain waveform, etc. So that's, let's suppose, call this XGW. Then we know the recession velocity of the groups of galaxies in which this NGC 4993 lies. Let's call it VR. Then you have a rough number for the average peculiar velocities. You don't know the exact peculiar velocity of NGC 4993. That is this average VP, right? That's what you have. So the data set that you have is something like this. And now the parameters of your interest are what is the true distance to this event, what is the inclination angle, because you saw that the amplitude depends upon both the distance and the inclination angles. Then the peculiar velocity will play a role because of these frequency shifts that you have. And then the Hubble constant. Right? The Hubble constant will connect the distance to these velocities in the end. So this is the likelihood. This is called the likelihood because you are trying to predict the data given the parameters. These parameters are things that you want to infer. Ideally, what you want is the probability of the Hubble constant given this data. That's what you want to reach at, right? Okay, so let's try to look at this particular beast here. So I can write this down as, so this is A comma B given some information. So I can write PA given this, this information times P of B given A, right? And so I'm now going to split this up. So you can see now it is XGW given this D cosine I, VP and H naught. But this XGW only depends upon D and D and the cosine I. So that's why I've separated it, left out these parameters, because if you are just given this, you should be able to predict this. And then you have a probability of the recession velocity given these parameters again. And then the probability of this V peculiar that you get given the actual peculiar velocity of the galaxy. And so this quantity here, you can write it down as H naught D. So that's the cosmological recession velocity plus the peculiar velocity. But it has an error bar of sigma square. So let's assume that this likelihood, it comes from a normal distribution. So, sorry, a Gaussian distribution with mean equal to this and with error equal to sigma square. And then similarly, what is this average peculiar velocity that you'll measure given the peculiar velocity of the galaxy? There is some velocity dispersion that is present, the error on the peculiar velocities. And so it's again a Gaussian distribution with VP as the mean and then sigma square as the error. So this allows us to write the likelihood. And so once you have the likelihood, you can compute what the posterior distribution of these parameters will look like given the data. Okay. So that's what you are interested in, H naught, comma D, comma cosine I, the V peculiar, given these measurements. And so you will see that there will be a prior on H naught that comes out. So this thing. Right. So P of A given B, if there is a H naught here, you will get a prior on H naught here. Right. So that's what you are getting in here. You will similarly also get priors on D, then cosine I, then VP as well. So all those are written here. All those priors are present. And then the likelihood term, which is this term plus this, okay, which was what we had written down here. This thing here is just one term, second term, and third term. Okay, is that okay? Yeah, so we had written down the likelihood P of B given A. So the data given the parameters that we have, that goes in here, these three terms. The priors, H naught, sorry, it's not written properly. I should have put it here maybe. So P of H naught, P of D, P of VP, P of cosine I. All of these are here. There's an extra term, this NS of H naught. This accounts for the selection effects, because what happens is you only try to measure the Hubble constant with events that you can actually observe. So the detectability of events can also depend upon H naught, and so that is another aspect that you need to put in the denominator for this. And these selection effects we'll get to in the next few slides as well. Okay, so once you have this machinery, let's suppose you set up some priors on each of these quantities. Then you can run through the likelihood and ask what is the posterior distribution of H naught. And that's what you get. This is the posterior of H naught as a function of H naught. And this is the distribution that you get from JW17OH17. Okay. The value from the Shoes collaboration at that point of time is given here with these orange 1 and 2 sigma regions, bands. And the value from Planck, the early universe, the prediction is shown here with this greenish band. And you can see that with a single event, GW 170817 was able to constrain the Hubble constant, something like this. Okay, so there is a wide tail here out to large Hubble constants, but there is a peak in the roughly the right region. Okay. Ideally, what you would want to do is to be able to distinguish between these two models. And so if you have many, many neutron star events, binary neutron star events for which you can get an electromagnetic counterpart, then the error bars on this measurement will go down further and further. And hopefully the hope is then you will get to like few percent kind of errors that you will start to distinguish between these two. So if it is a systematic effect that we see this Hubble tension because of some problems in the distance ladder, then you will see that it should peak somewhere around this green band. But instead, if there's something wrong with the cosmological model itself, then you will see it peak around the orange value, which means that somehow the universe is expanding faster today than what is predicted by looking at the early universe. And so that will be, again, a big thing, right? So that's the reason why people are looking for these kind of GW 170817 like events. Okay, so then, as you know, the amplitude of gravitational wave events is related both to the Hubble constant because through the distance measurement, as well as the inclination angles. And so instead of showing this marginalized contour where I only focused on P of H naught by integrating over all possible values of D and cosine and VP, instead of that, I can show you the posterior constraints on H naught, comma cosine I. Okay, just to show you this degeneracy between the Hubble constant and the cosine of the inclination angle. So that is shown here. So this is the two-dimensional posterior. And you can see that there is indeed a degeneracy like this. So if there was a way to get at the measurement of the cosine of this inclination angle better, then you can put a better constraint on the Hubble constant as well. Okay. But if there is no such information, then you are left with this kind of a degeneracy that exists. Okay. Yeah.
Because D cosine are all are calibrated by the distance ladder itself, right? I mean, there is no CMB information. Like when in the priors you have chosen the D cosine I or
no, so these priors, people try to make sure that they don't include this kind of electromagnetic cosmic distance ladder kind of information there when they use the priors. Okay, so that you are free from those electromagnetic kind of assumptions. But the rest of these things, these are direct recession measurements, right? So velocity measurements. So they don't, again, involve the distance ladder necessarily.
So this recession velocity should be taken as a mean and the sigma would be taken by the instruments one, right?
Yeah.
So, okay, no.
Yeah, So there's no error bar because of the distance ladder necessarily here. This is just velocities, not distances went in. So they try to be careful not to introduce EM information. Because if they do, then again, you will get into exactly the kind of trouble that you're talking. Okay? Okay, so this kind of a thing, now that at least I had told you what the dependence of these different polarization amplitudes are on the inclination angle and the distances, you should try to verify that indeed you are expected to see a degeneracy like this. Okay, you go back to the lecture notes from a day ago or so, right, from yesterday, right? And you should try to convince yourself that indeed this degeneracy should be present and in this direction. Okay, so then if you can measure the inclination angles, you can get a better handle on the Hubble constant. So there is a lot of effort in the community to try to use the light curves of the gravitational wave event that are seen in order to figure out what kind of inclination angles are possible. And so when you have the binary neutron star event and you can follow it up, so there's lots of effort, modeling effort into like these jet and cocoon models in order to try to understand where exactly is this inclination. Once you combine that information, then you can get better constraints on Hubble constant. There's another interesting thing that you can do, which is to try to look at the motion of the jet that came out from this event, and try to track its motion using something called very long baseline interferometry. So these are radio telescopes all over the world, which are situated, and because they are all over the world, the resolution is quite good. And so if there are blobs in the jet that are moving, you can track them with very good accuracy. So that's what they did. So this is, for example, initially where the blob was and where it went on later after us. Sorry, maybe here it was initially and then it went on to being at a different location. And so these kind of offsets you can use in addition to the light curves to try to model what the jet inclination is. Yes, yes. Yeah, so I will come to that. I'll try to get to that. So when they observed this event, they saw that if you know roughly what the distance is to NGC 4993, you can calculate what this distance would correspond to. So given this angular difference, what the distance it corresponds to. And if you know the distance and divide by the time taken to go from for the jet blob to go from here to here, and then you see that it is actually moving with faster than speed of light. Of course, this can't really happen. But I wanted to tell you how exactly this thing happens. Okay, why do you see something which seems or which gives an apparent superluminal motion? So this is just to show you how the jets look like. So these binary neutron stars, they are emitting gravitational waves coming closer and closer to each other. And then after they merge, then there is a jet which gets launched. And you observe this jet at a certain angle. Right? So this jet is emanated perpendicular to the axis of the merger. And so then you see this event at a certain axis. And so that inclination angle is something that you can measure if you can look at this jet. So that's the idea, right? And so that's what was done here. So let's try to understand superluminous. This is not the jet from GW 170817. This is a quasar jet instead. So what you are seeing here are pictures of this jet taken with VLBI. Okay, not again GW 170817. This is just to explain to you how this superluminal motion works. So this was taken early in the 1990s. Okay, so maybe 1991 or so. And then after there's like an intensive period of monitoring that has happened for this jet up to 1998. So you can see this VLBI images. And you can see this blob. So this is the core of that jet. And this is that blob. And this blob is basically moving outwards. So you can measure in arc seconds how much this blob has moved. If you know the distance to this object, then you can convert it into light years, how much this motion is. Okay? And you can work out what is the time. Time taken by the jet to move, the jet blob to move from this position to this position. So why does this give you superluminal motion is just quickly we'll try to understand. So let's look at the core of this jet. So let's suppose it is here, this core is here. Okay. And then there is a jet which is launched at an angle theta with respect to the line of sight. So let's suppose this is the line of sight here, this straight thing. So you are somewhere like really, really far away. You're looking at this jet. So when A was imaged, when this blob was imaged, it was here. Okay. And in 1998, this same blob, it had traveled to this particular location, right? let's suppose the speed of this jet is equal to v, where v is equal to c times beta, beta less than 1, of course, right? And so between A and B, there is delta time which has gone. And so it should have traveled a distance beta c times delta t, okay, in the frame of the jet. Okay. So if indeed it takes a time delta t for this blob to move from A to B, then this is the time, this is the distance that the jet would have traveled, right? So what is happening is the radiation from A was received at a time, say Ta, but the radiation from B, now it has to travel a lesser distance to come towards you, right? Just because the blob has moved from A to B. Okay. And so the time delay that you will observe between when this, when this image was made and this image was made, it is related to the fact that first of all, A takes a longer amount of time to reach you. And there are two components. One is A was emitted before, and then it took some time to reach you. And then B was emitted later, but it took lesser time to reach you compared to what when A was emitted. And so what happens is the time that you observe, okay, between A and B is different from this kind of a delta t time that has gone in between when the blob was at position A and at position B. Okay. So when you do this calculation, you can show that you can get apparent superluminal motion, even though the jet is actually not traveling faster than the speed of light. Okay. So this is just because of these time delays. And so this, again, I will leave it as an exercise. This is simple trigonometry. So beta c delta t. There's this cosine of the inclination angle which goes here. So the distance by which B has to travel less compared to A, or the light from B has to travel less compared to A, will be beta c delta t times cosine of theta, right? Yeah, so the jet is then assumed to be perpendicular to the direction of the plane. Yeah. Okay, so if you have this theta, then you can relate this VLBI motion as well, right? And so it turns out that the observed or the apparent velocity that you'll get, it will be related to the actual velocity times these angles, okay? And so if you can measure this motion, and if you can model the light curve, then you can put a better constraint on the inclination angle. So that was also what was done for GW 1708-17. And so if you just take the gravitational wave events, this is distance versus the inclination angle posterior. Okay, so this is not showing the cosine I. This is distance versus inclination angle. It looks like this, just with the GW event. Now you combine the VLBI plus the light curve data. So if you just take the VLBI plus the light curve data, you can see that you can very well measure what the inclination angle is. So now you combine both of them, the GW as well as the VLBI data. Now you lie somewhere here. So you get a better measure of what the distance as well as the inclination angle is. So you do that. If you just use GW event, then this was the posterior that was found. But now you combine it with the VLBI plus the light curve data, then you get a posterior which is more peaked. Okay? And this is exactly what we want. Again, not good enough to distinguish between these two models. I mean, some people would say and put a lot of faith into seeing that the peak is close to Planck, but you should not do that. Right? Posteriors are posteriors for a reason. There is finite probability that it could also be this. So we have to wait. We have to gather more and more data, and then that will help us hopefully break these degeneracies or try to understand which of these is right. Okay, Is everyone with me until here, right? So we had the GW170817 event, found its electromagnetic counterpart, carried out a Bayesian analysis in order to figure out what the Hubble constant is. We saw a degeneracy with the inclination angle. And so there were measurements which were also being done to constrain also this inclination angle separately using VLBI plus the light curve data that was present for the electromagnetic counterpart. And that allows us to get to a Hubble constant, which looks somewhere. Okay, this is quite impressive, by the way. I mean, in the early ages, when we were trying to discuss about the Hubble constant, you saw Hubble had gotten like a value of 500. And then even maybe 70, 80 years ago, there was a confusion whether the Hubble constant is actually 70 kilometers per second per megaparsec or 50 kilometers per second per megaparsec. So with a single event, you can, I mean, 50 is quite far beyond, 100 is quite far beyond. You can see with a single event, you get quite a good posterior, right? And there's no distance ladder involved at all in this. So it's quite impressive what we can do with a single event. Okay, so one of the things that I told you is that peculiar velocities, sorry, yes. So I actually have not gone through what this hydrojet, this must be some other modeling, I think, which was done. So, yeah. I think the reason why I wanted to focus because VLBI plus the light curve data give. Okay, so as you saw, there is an importance to measure also the peculiar velocities of galaxies, especially in the nearby universe, if you want to get constraints on the Hubble constant, given the gravitational wave data. So how do people really measure these peculiar velocities? So for peculiar velocities, what people typically do is they look at some galaxy scaling relations, okay? And in particular, their residuals. So galaxies are known to follow certain scaling relations. This is the Tully-Fisher relation. So this is the luminosity of galaxies as a function of the circular velocity. So how quickly the gas rotates around this galaxy at about 2.2 disk scale lengths. Okay? So if you take a disk, you can fit it with an exponential profile. So there's exponential minus r by re. That RE is called a disk scale length. And so people measure this circular velocity at 2.2 times the disk scale length. Okay? So if you, so this is some combination logarithm of 2 times this velocity minus 2.5. So it doesn't matter, is the velocity here on the x-axis. And then the y-axis is the magnitude of this, or the brightness of these galaxies. So this follows quite a tight relation. This is called the Tully-Fisher relation. In fact, it is so tight that if you, I mean, there are also error bars which are not shown here, but if you put the error bars, and you can ask what is the intrinsic scatter of this relation, and the intrinsic scatter is very difficult to measure because most of the error bars that you see on the Tully-Fisher relation are just dominated by the measurement errors themselves. Okay, so the intrinsic errors, the intrinsic scatter in this relation is quite small. Why it is the case is another mystery. So we will not touch upon that right now. But this is also a consequence of the virial theorem in some sense. Okay. So let's suppose you have these kind of relations. Then there is another relation. So this is for disk galaxies. So this is if you have pure exponential disk. This is with galaxies which have both disks and bulges, and then you can ask whether you should remove the light from the bulges or not, and so on and so forth. So there are more complications there. But the main thing is you have such a relation for spiral galaxies. And then if you look at elliptical galaxies, then they don't follow a simple relation like this kind of velocity. So instead of having the gas velocity, you have the velocity dispersion of galaxies that you can measure. And then there is instead of an absolute magnitude, what they do is they look at the magnitude per square arc second that comes from these galaxies. So the surface brightness of these galaxies. So the fundamental plane that is talked about is a relation between the size of elliptical galaxies, the surface brightness of these galaxies, and the velocity dispersion. Okay? All of this related to the virial theorem as well. So now it is in 3 dimensions. Okay, so it's called a fundamental plane because it's not a single line. Okay? So this is the fundamental plane shown in different kinds of projections, of course. So again, you can see it's a fairly tight relation. Okay? And so now what you can do, yeah? Yes, so this is the velocity dispersion of stars within the galaxy. That's all. Okay, this was the velocity of the gas which is going out at 2.2 D scale lengths. And this is the velocity dispersion of stars within the galaxy. Okay. The velocity dispersions, you take a spectrum and then you look at the width of features within the spectrum. That tells you the velocity dispersion. You don't have to measure individual velocities of stars. No, sorry, I did not get to that. Okay. Okay, so now that you have this, you can try to think about how peculiar velocities can affect these measurements. Okay. So first of all, let's look at this plot, right? The velocity 2.2 peculiar velocities will, there is a rotation velocity that you're trying to measure, right? So if there is a peculiar velocity, what will happen is this galaxy is moving out. But when I want to measure the rotation velocity, I can measure it from one side and the other side, okay, and then take an average. And so this thing, the systemic velocity of this galaxy will cancel out. So I don't need to worry about that for the x-axis here. Okay. But for the y-axis, what is on the y-axis is the absolute magnitude of the luminosity of a galaxy. That depends upon the distance that you put, right, for this galaxy. And if the distance is coming from the redshift itself and a cosmological model, then if the redshift has an uncertainty due to the peculiar velocities, then you will move up and down compared to the true relation, right? Because you will either infer a larger distance or a smaller distance based on the redshift that you have measured, right? And so that will cause a scatter, an extra scatter in these magnitudes. Okay. So now what you can do is you can statistically try to measure this peculiar velocity effect. You won't get it right necessarily for one galaxy. Okay, but if you have a bunch of galaxies in the sky located in a similar region, now you average over the residuals in these relations, then you can roughly understand what is the peculiar velocity in that direction. Okay. So this is done. So in the case of the fundamental plane, there is the size of the galaxy, which is here, right? And the size of the galaxy is equivalently affected because of the peculiar velocities. Because you get a wrong redshift, you infer a wrong distance, and so you convert an angle into the size of the galaxy in a wrong manner. Okay, so the residuals here in the fundamental plane again also give you information about the peculiar velocities. Not for individual galaxies, but once you have a big survey of many galaxies which look at these relations, then you should be able to roughly figure out what the peculiar velocity field looks like. Okay, on large scales, averaged on large scales, it will be okay. So that is what is done here in the neighborhood of the galaxy, of our own galaxy. I think partly the reason why this thing is empty is because it's the plane of our own galaxy where we cannot make measurements. But then away from the plane of the galaxy, you can see this peculiar velocity field that people have worked out. Okay, so how wrong you can get distances based on redshifts, how wrong they will be if you measure. So this is like a 3-dimensional field. So I'm just showing you a rough map of what this looks like. And so this is how you do the peculiar velocity measurements. So you take these peculiar, again, you can see there is a large blob, right? And that's the reason why the uncertainties are also large. You cannot do it like at exactly the location of the galaxy, what exactly it will be. But averaged over large scales, you will roughly know what the velocity fields look like. Is that fine? That's about peculiar velocities. As you go further and further out, then it becomes less of a problem, these peculiar velocities. There's another thing that people try to do, which is they will take observations of galaxies that are seen in the nearby universe, and they will try to reconstruct the cosmic density field, okay, of what these galaxies, what is the dark matter density or the total matter density in which these galaxies lie. And from that also work out, from this reconstructed field, what should be the velocities of these galaxies, okay? So that kind of reconstruction techniques are also used in order to infer the peculiar velocities. Again, we will not go into the details. I just wanted to mention that that's another way that people look at this problem. Okay, so that was about 1708-17 that I wanted to tell you. Yesterday, we had talked about this stellar graveyard kind of picture as well. This is picture I lifted from Wikipedia. For the events that have been detected until 03, the 04 candidates, I think, are down below here. They are not been put on this particular plot yet. So this is the solar masses of these black hole candidates, and then of the candidates that were detected, and then this is the distance at which these events were detected. So again, when someone is telling you the distance, there is an assumption of a cosmological model right now here, right? And then what you are seeing are basically the mass of the smaller object here, the mass of the larger object here. The chirp mass is somewhere shown here in green. Okay. And then basically this is the zoo of events that LIGO, Virgo, Kagra detectors have found so far. And so the problem is there are many, many events that have been detected, but there's only one electromagnetic counterpart that we have found so far. So the question is how to use this zoo of events in order to do cosmology. Okay. Of course, it's not going to be as perfect as what you can do with an event which has an electromagnetic counterpart. The question is, does the statistics somehow help you out? And the fact that you have so many of these events, roughly a factor about 1:50 to 100, you know, more binary black hole events than events which involve neutron stars. And so the question is, can we use these? And even if there are some neutron star events that have been detected, we have not yet found the electromagnetic counterparts. So there is a neutron star black hole kind of a merger event. People tried to look for the counterpart of this. It's not conclusive. Okay. So in the absence of electromagnetic counterpart, what should we do? Yes, sorry. Right. So these are distance measurements from GW events. So what you measure is basically m times 1 plus z, right? The chirp mass. And so there will always be a degeneracy, no? Because the waveform, or no, maybe not, right? You get directly the distance. Sorry. So there's no assumption there. You're right. Absolutely. Sorry about that. Yeah, in the masses, there will be an assumption because these will be the source frame masses, right? Sorry. It's the opposite thing. Yeah. Which one? No, so I think both of these black holes are shown, if I'm not wrong, okay. Both of these black holes are shown. I think it must have to do with when M1 and M2, what is mass ratio, right, exactly. What is the mass ratio? That determines how close you will be. I suppose, right? That's what. Yeah. No, so again, I mean, it depends upon the details of these events. And so you get the M1, get the M2, calculate the chirp mass, and you will see where it lies. Right? Yeah. So I don't know. I mean, again, this was from Wikipedia, so I don't know how exactly they made, whether they actually took the posterior of the event or the maximum likelihood, the maximum of the posterior of the event. What exactly is done, I'm not sure. But what I wanted to show is that there are many, many binary black hole events compared to the neutron star, or compared to the events in which neutron stars are involved. And so that's the reason why we want to work with these kind of events as well. So how do we do it? Okay, so that's the question. So how can we do Hubble constant from binary black hole events? So you know that there is a localization region that you can see, large swath of the sky. So these merging binary black holes will give you the luminosity distance, and the redshift information is not readily available. So you need to basically find some redshifts here. If you can find the redshifts, then you should be able to get the Hubble constant. So the question is how to find the redshifts of these binary black hole events. So one of the ideas is you consider all possible galaxies which lie in this localization region, and then try to estimate the Hubble constant from there. Okay. Yes. 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 Yeah. Yeah. That's right. Okay, so there was a paper which was written in 1986. So this is like way before gravitational wave events were discovered by Bernard Schutz, determining the Hubble constant from gravitational wave observations. And this forms the basis. So the idea was, even if you don't have a counterpart, you should be able to measure the Hubble constant. So how does this idea go? So the idea is, if we accept that this h naught is less than some value, say h max of 120 kilometers per second per megaparsec or so, then the error box that lies, you can try to find out if there are galaxies within this error box. And then you can assign the Hubble constant based on the redshifts of galaxies which are within this error box. Okay. Now, of course, the gravitational wave event cannot lie in all of these galaxies. It will lie in one of these galaxies. And so what will happen is you will get the right answer for only one of these objects that lie in the error box, not for all. But the others will be kind of randomly distributed. And so now, if you, instead of having one event, if you have multiple events, then there will always be the event which gives you the right Hubble constant, and the others will be quite random. And so you can pick out the correct Hubble constant in this way, statistically, if you have many, many events. So that's basically the gist of it. Okay. And so this was properly shown how it works in simulations. This was using LISA kind of error bars by McLeod and Hogan in 2008. So what they did is, if you have just even a single interferometer, you detect the gravitational wave event, you roughly know, you take the galaxies, and this is LISA kind of interferometer. So you take the galaxies, and then within the localization region, again, assign the Hubble constant based on the redshifts of each of these galaxies. Then what you will get. So you can see that if you have many, many events, so this is roughly the number of events that you have, I think, then you can start to see that the true Hubble constant emerges out, basically. If you have multiple interferometers, then what happens? Different number of boxes, etc. But the idea is you try to utilize the fact that you can survey galaxies in a region, whatever your localization region is, and you can figure out their redshifts. And if you can measure their redshifts, then you should be able to figure out what the Hubble constant is. Okay, so that's the idea. So currently what is being coded up in the LIGO-Virgo-Cabra collaboration is a method called statistical host identification. So it borrows from these methods that Schutz and McLeod and Hogan had. What it does is it ignores the clustering of galaxies. Okay, so galaxies are not distributed uniformly in space, they are also clustered. So this introduces some more complications, or in fact, some more information that you can utilize. And we'll see how to do that on Friday. Okay. So for the moment, we ignore the clustering of galaxies. And then, as I said, if you assume the potential host of the GW event is in the galaxy catalog, then the method of Schutz et al. Will work. It's not a problem. But there is a finite probability that the galaxy which acts as the host of your gravitational wave event is not in your galaxy catalog. And the reason why it is not in your galaxy catalog is just because when you point a telescope at a certain region of sky, you cannot observe all the galaxies that you see. Okay? It's similar to what you do. You go and see in the night sky, you try to look at the sky. You cannot see galaxies necessarily with your naked eye, right? Unless you go to a very remote site, you can see Andromeda, but not the other galaxies necessarily. And so each of the telescope has its own limitation. Just like your eye has limitations, the telescopes have limitations. There is a finite amount of integration time that you can use. And so you can only see galaxies up to a certain flux limit. Okay? And so there will be certain galaxies which will always be missed. And nobody tells you that the gravitational wave event cannot happen in that galaxy. Right? And so you have to account for this kind of behavior as well. Okay? So these incompleteness which is present in real galaxy catalogs, that also needs to be accounted for. So the current LVK method that is there, it's called statistical host identification. It will try to figure out what is the probability that the host is within your catalog. If it is within the catalog, it uses all the redshifts and then tries to figure out what the Hubble constant could be. But it also accounts for the fact that the galaxy catalogs are incomplete. How we do this, we'll go into the mathematics of this tomorrow. There is another method that you can use, even independently of whether you have the redshifts of the gravitational wave events or not. Okay. This method is called a spectral siren method. Okay. So how does this work? So the assumption, the main key assumption in this method is that the distribution of the masses of the gravitational wave events or masses of the compact binaries which undergo the mergers, the distribution of these masses is invariant as a function of redshift. Is this true? I don't know. Nobody knows. But that's the working assumption that you start with. So far, whatever people have tried to look for, they have not seen any evolution yet. Okay? That doesn't mean it does not exist, but we can start with that assumption. Okay? So this is the assumption that you can start with, that there is an intrinsic distribution of masses. Not necessarily it looks like this. I'm just showing a cartoon picture here. Then what will happen, right? So let's suppose you have gravitational wave events, many of them that you have detected. And let's suppose you can bin them in luminosity distance bins. Okay, so let's suppose this is distance bin 1, this is distance bin 2. Okay. Now, what you measure in the detector frame is the masses in the detector frame. So you don't measure the actual source frame masses, you measure the detector frame masses, which are 1 plus z times the source frame masses, right? So what will happen is, if you now make a probability distribution of the detector frame masses, then it will be something else. Okay? So it will be shifted compared to the intrinsic distribution. The amount of shift that is there can tell you the redshift of these events. Right? Okay? So if there is an intrinsic distribution, the detector frame masses, and you plot their distributions, it will be shifted compared to this intrinsic. In fact, you don't even know the intrinsic distribution, but it will be shifted, right? And now if you go to luminosity distance bin 2, it will be even further shifted. So the fact that there is this shift, it will allow you to figure out what are the redshifts of this. So that's what is called a spectral siren method. No, so this, I'm talking about the intrinsic, this is without the measurement errors. Once you have the measurement errors, then you have to deal with all those problems. Okay, so that's exactly what is going to come next. What happens in the presence of errors. Okay.
Rohit Kumar, can you please mute yourself?
No. There is no luminosity assumption here. You remember from the chart, you can actually figure out what is m times 1 plus z. Right? So what you do is, whatever luminosity distances are measured as we looked at, right? And so you take those luminosity distance, you make bins. So you have now multiple gravitational wave events in the same bin. You make a distribution of the detector frame, so m times 1 plus z. That is what is shown here, right? So the distribution of m times 1 plus z will not be the same as the intrinsic mass distribution. But given that all of these are at luminosity distance bin 1, all of them should have roughly the same redshift. And so the whole thing should have shifted by 1 plus z. How much it has shifted, if you don't know the intrinsic distribution, you don't know. But this would have shifted differently compared to this. No. We have the same luminosity distance for these events. So that's why they should roughly be at the same redshift. Of course, it depends upon how big this bin is. And so all the errors you have to deal with. I'm just telling you, in case you had gravitational wave events which are happening at the same luminosity distance, right? You found them, then the distribution of those masses will be shifted. Okay? So this gives you a handle on the redshifts of these events. And if you can find the redshifts of these events, then as I said, you can get the Hubble constant. Yeah. Well, I mean, we don't know really what the true distributions are. But people within the collaboration have also worked out what these distributions may be under the assumption of a fixed cosmology. Yeah, and then they see some distribution. It has multiple peaks, sometimes maybe power law plus a peak. There are multiple possibilities that are there. But they see that there are features in this distribution. Remember, if this was completely featureless, then it will be very difficult to do anything. But the fact that it has features, that has allowed us to now try to use it in order to do cosmology. So it is phenomenological, as anyone would say, right? There are critics of this method, and of course, the critics should be also taken seriously because, see, we want to eventually get down to 1% precision. Will we be ever able to tell whether the intrinsic mass distribution varies by within the percent level margins or so? I don't know. Okay, so that is one thing that you have to keep in mind when people use these methods. So you. It will completely degenerate, no, with the distance measurements, with the redshift measurement. Sorry. So you can always cook up a model which does something crazy, and then it changes the intrinsic mass distribution in some way, which then compensates for this, and then yeah. So we have to be careful about these things. I mean, at least you have to keep it in the back of your mind that there are people who criticize these methods, and there are good reasons to criticize. Yeah. Okay. So how do you measure the mass distribution? So, I mean, the way I told you, it is as simple as, okay, you measure the chirp masses, make a histogram, and you see it, right? But that's not as simple as that, just because there are error bars on all of these measurements. So when you measure these M1s and Qs, you see that huge error bars in these measurements, right? And so Q is basically the mass ratio, right? M2 divided by M1. You can see large error bars in M1 and M2. Even the chirp mass, it has certain error bars that are there. And so what you have to do is to figure out what is the true distribution, the true underlying distribution, given the fact that you have noisy measurements. And so this is a Bayesian, again, a Bayesian kind of problem. You want to figure out the parameters that describe your distribution, given the data measurements that you have. So how do you do that? So that's why, again, we come back to a Bayesian analysis that you will have to perform. So what will be this lambda? It will have some cosmological parameters, the parameters of how the rate of these cosmological events change as a function of redshift. You will have how the shape parameters, so how the shape of the mass distribution looks like, that as well. So you would ideally want to constrain all of this. Okay. And so what you want to do is this parameter set, P of lambda, you want to work out what are the parameters given the data measurements that you have. So P lambda given DI. DI is set of n gravitational wave events that you have measured. And so using Bayes' theorem, this will be probability of the data given this parameter set, the prior probability, and then this evidence here. Just the Bayes' theorem rewritten. And so what you will get is dn by d theta. So the measurements that you do, what are the individual parameters of events that you measure? So this is this theta. And so that will have a certain amplitude n and a distribution, so shape, right? So there is how many events you see and what is the mass distribution of these events. So the mass distribution parameters, let's put it in lambda prime, and the number itself is in n. Let's assume cosmology is constant for the moment. Okay. So let's ignore even cosmology and even the normalization. Let's suppose you just want to figure out what are the distribution, the intrinsic mass distribution of our events. Just a simple thing. Now, let's even ignore the measurement errors to start with, right? Even if you ignore the measurement errors, then the probability that you get for a theta given the shape parameters lambda I, what should it be? Let's suppose there is only one single event, theta I, right? Then it will be the population parameters of, like, what is the measurement of whatever m that you measured for that event, right? Divided by all possible values that you can get, right? That's how you measure probabilities, right? If you have a dice, you roll a dice, you want to ask how many times will I get one? You divide by the summation of all possible values, right? So in a dice, you can have 6 different possibilities. So 6 goes in the denominator. That's the denominator here. All possible values of theta, right, that you are integrating over. And then this probability of a particular theta that you have. Right? Now there are n different events. All of them are independently measured. And that's why you will multiply them to get the total probability of all the events that are possible. So this is the likelihood of the measurements of parameters. So these theta i's are m1s, m2s, the spins and whatnot, right, of each and every parameter. Okay. And so this is how you can work out what is the likelihood or of observing a particular set of parameters given the shape parameters. And this ignores all the error bars right now. Even in the absence of error bars, what you have to worry about are selection effects. That whatever you are seeing, you only select certain events. Okay, so imagine if there was a dice which we are rolling and you wanted to figure out what is the probability that you get 1. But when I give you the rolls of these dice, I never give you events which have 5 or 6 turn up on them. Okay, then the probability that you will infer will actually be different, right? And so because I have introduced a selection effect on top of it, I have removed certain events. Okay, so that is something that you have to also take care of. So how do you take care of that? You multiply the probability of getting a theta given your shape parameters by what is the detection probability for this theta. Okay, so whether I'm going to show you this event or not, right? So in the case of, again, this case, when I throw the dice and I remove out 5 and 6, then the detection probability of theta I will be 1 for 1, 1 for 2, 1 for 3, 1 for 4. But then for 5 and 6, the detection probability will be 0. Right? And so, but similarly, now when I normalize, I will also have to take into account this detection probability so that I figure out what is the true probability of the events that I see given the shape parameters lambda. If I don't take into account this, I will get wrong numbers. Right? I would have inferred, if I didn't take into account this detection probability, I would have inferred a wrong value for the probability to get a 1 on the dice, for example. Right? I'm sorry? So all of these are normalized, and that's the reason why there is an equality here. But No, so let me come to this equality one by one. Right? So this is clear, right? Where this comes from. So now you remember that these theta i's are the gravitational waves that you actually observe, right? So they should already pass the detection probability threshold. The probability for detection of those events that you exactly observed should be 1. And that's the reason why this has been removed. That's all. Okay. So that's where this thing went, p det of theta I. Okay. And so this p of the probability distribution of getting any theta I given the lambda prime, it looks something like this. Okay. But we are not interested in the likelihood, but likelihood is the first step to write down the posterior. And so we'll then write down the posterior after this. Oh, we are at the end of the lecture time. So I will stop after this slide, if that is okay. Yeah. So what is this detection probability? So typically what will happen is you will measure something like the SNR of your events. And you will say that only I will select events if they cross a certain SNR threshold. Right? And so what is the probability of detection for a given parameter set theta? That will be all possible data vectors that you can draw given your theta. So now we are going to account for noise. So let's see what noise does to these things. So for all possible, for a given possible value of theta, there may be different data vectors that you draw given the noise realizations. So you integrate over all possible data vectors, and that will give you the probability of detection at a given theta. And when you integrate, you don't integrate over everything, you only integrate over events which cross your threshold. Okay. So once you do that, then you can get the detection probability. So this thing, you can write it off as, so the integral that is done only over the threshold, you can write it off with this kind of a detection probability for I, where I will be equal to 1 if you detect it, is equal to 0 if you don't detect it. And then the integral goes over all possible data realizations. Okay. So this is the detection probability itself. Now what you can do is you can take this. Okay, let's look at the denominator here. This denominator here. So you have the p det of theta. So now you plug it in. So you plug this integral inside here. Okay. So that is this dd, which is here. You can see this pd given theta, which is here, and then the p pop of theta carried out over the threshold, right? And then you can take this integral inside, take the theta integral. So you're just reversing the order of these integrations. And then what you get is the detection probability itself, which goes in here. Okay. So this p det of theta, which goes in here. So this quantity is this alpha of lambda. So that is in the denominator here. And so the probability that you get a data given lambda prime will be given by this kind of an equation. So this accounts for the selection effects, this denominator that you see. So how do you go from this to the probability distribution of the parameters which describe the data? We'll take a look at it tomorrow. Okay, so let's stop here. And then maybe we can come back after the tea break, right? Yes.
All the questions.
Yeah, I mean, we have anyway, I try to answer questions as they come in. Yeah. But in the coffee break, I'm available, of course. Thank you.
Thanks.